We have been studying the motion of particles and rigid bodies in this course so far, and my goal in today's lecture is to give you a little bit perspective on what the next steps are in studying dynamics and especially dynamical systems. I promised you guys during the course that I will take the time to at least give you a little bit of introduction on nonlinear dynamics and introduce a couple of good resources to you guys. And this is because I am assuming that you are taking this course, the intermediate dynamic course, maybe because you are more interested in these topics. After all, you all had the dynamic course and you took this course because you wanted to learn more on this stuff, or at least some or few of you did. So also another reason is that the nonlinear dynamics touches on my area of research, and we have a good faculty members that are in this field here in Binghamton University in vibration, nonlinear dynamics, acoustics, MEMS, which stands for microelectromechanical systems, and we have good facilities and labs also at BU. So just in case if you're considering going to graduate school and study more on dynamical systems and vibrations, I would like for you guys to have a taste of what you will be studying and doing research on. So the other thing is that at the end of this course, at the end of this lecture, I introduced the Euler-Lagrange approach to derive the governing equation of motion, which you are going to use in future courses such as mechanical vibration. So, and as we will see, this approach is a very powerful method to derive governing equation of motion for mechanical systems, for dynamics of mechanical systems, especially in vibration. And I will say that why I'm kind of like separating vibration from dynamical systems in general as we go along this course. So, and most of the things that we are going to talk about today are related to vibration. So I think at the end of this lecture, we will be at a good place to introduce the Euler-Lagrange approach. So with all this being said, let's get started on today's topic. So as I said, so far we have had the dynamics of, we have studied the motion of particles and rigid bodies, and all of the analysis that we have had, all of the problems that we have been solving is on the dynamics of a particle or a rigid body at one particular moment, at just one instant, one snapshot in time. But as you can tell, that's not the case. We can study the motion of a particle, a rigid body, during time, as time passes. Study the trajectory of a particle or a rigid body. So in those cases, we have to have an equation for the, let's say, trajectory of a particle, or studying the motion of a rigid body that is valid for all times. And that is going to be basically, again, the same, the Newton's equation, but we have to kind of like derive the equation in a general case that is valid for all time. So we can say that so far we have had just F equal to MA, and let's say, for example, we are in 1D, just to make it easier, but all the things that we are saying is just true for a general case. For 1D, for a particle that is just moving in 1D, and let's consider that direction, one dimension, just in the x direction, we can say that sum of all the forces in the x direction is equal to m times ax, acceleration in the x direction. Or I can say m d to r dt squared. the second derivative of position vector with respect to time. And position vector for a particle in 1D, we can just say that r is just equal to x in the I direction. And because we are writing down the scalar version, we can say that this is equal to so I'm not going to write down the I anymore. This is basically sigma fx in the I direction, ax in the I direction. But let's go with the scalar format. So this would be the second derivative of x with respect to time. And we have been just studying this equation so far, but just at one moment. So at, let's say, t equal to t1 at a constant time, or t equal to 0, we have been using this equation. We sum up all the forces, and usually we have a problem that we have to kind of like relate the acceleration. We don't have the acceleration or some of the forces. We have other constraint, and basically just using this equation, basic equation, and other constraints that we have, we solve this again at one moment. But you can see that this equation is true for all the moments. So for at all the moments, the sum of all the forces on a particle is equal to its mass times its acceleration. And if we consider that version, not just at one snapshot of a time, this is basically a differential equation, an ordinary differential equation, or we call it ODE, ordinary differential equation. So it would be sigma f of x is equal to m, and this second derivative of x with respect to time, we show it with double dots. So one dot is just the first derivative. The second dot, that means that the second derivative. It's kind of a little notation that makes writing the equation easier. So this is a differential equation, ODE. And basically, you are going to study this equation for a particle in 1D in mechanical vibration course. So all you're going to study in mechanical vibration course, not all, but most of the stuff would be basically on the study of this equation for a single particle in 1D. The only time that we had a differential equation in the course was when we were studying the motion of a particle under central force. So when we had motion of particle under central force, that was the only time that we had an equation. We derived the equation for a planet orbiting Sun, or a satellite orbiting Earth, or any particle basically under a central force. We derive an ODE, a differential equation, and we saw how we can solve that. But aside from that, everything that we had in this course was just basically in this equation in one particular time, not in all times. But if we consider that equation in all times, we are going to have an ODE. And that's basically a dynamical system. So for a dynamical system, a kind of like a very rough definition would be a system that has a property that changes with it changes with time. So a dynamical system is a system that one of the property of the system, or it might be a couple of properties, they would change with time. So a property of system changes with time. And you can see that this is a very, very general definition. It's not just for dynamics or mechanics or vibrations or these kind of topics. It's any system that we have that one of the properties changes with time, that's a dynamical system. And the study of these systems are basically all related to each other, because they are all going to be they are all going to be modeled as a differential equation. So as an example for dynamical system, we can say that the weather is a dynamical system. So forecasting weather is done through a set of differential equations, a mathematical model that is differential equations, and that's basically how they forecast the weather changes with time. And they forecast that tomorrow what the weather is going to be, or the day after tomorrow, and so on. So that's one example of dynamical systems. Weather changes with time. Another example of dynamical system, which we are familiar with, and you are going to be studying this extensively in mechanical vibration, is just a mass single particle that is attached to a spring, and it is kind of like going back and forth here, oscillating here. So the position of this particle changes with time as it is oscillating. So that's a dynamical system. That's a recipe for dynamical system. We are familiar with the ordinary differential equation that models this system. Maybe not this system, but again, it is going to be very, very similar. A differential equation, basically, that models the weather. Another example for dynamical system is, let's go to heat transfer, for example. So in heat transfer, so it's a very, very kind of like wide topic. So in heat transfer, let's say you have a rod, for example. So you have a one-dimensional rod that you have kind of like, here the heat doesn't transfer on the side. You have insulator here, and let's say you put one side of this rod inside boiling water. So here, boiling water. So the temperature here is just, for example, 100 degrees. And on the other side, you put the other end inside iced water here. So iced water. I don't know if you guys have already had the heat transfer course, but basically it's going to be a studying of systems like this. And here the temperature is just 0, for example. So the temperature in this rod here at each point depends on time. So the temperature in the rod basically depends on position along the rod. So let's say this is X axis. And also at each position, the temperature depends on time. So at the beginning, when you put this end in the boiling water, the other end in the 0 degree water, so you're gonna have the heat transferring from this side to the other side. But after a while, you're gonna reach equilibrium point. So until you reach equilibrium point, at that point the temperature at each point would be constant, doesn't change with time anymore. Up until that equilibrium point, basically you have a dynamical system because the temperature at each point changes with time. So here, basically you have if we show the temperature in this rod with T, it's going to be a function of two variables, X and T. And basically the differential equation that you get on this function for this dynamical system would be a partial differential equation because the function is a two variable function. Another example of dynamical system is a spread of a cancerous cell, for example, in a body. So a spread of cancerous cells in body. Basically, the way that they model the spread of cancerous cells, again, is just through a mathematical equation that shows how, for example, the number of tumor or the size of a tumor or the number of cancerous cells in the body changes with time as the disease progresses. And if you just do a little bit search on this, you find many papers that they show the mathematical equation, the differential equation for that case. As a matter of fact, I have done that. So let me show you, for example, here I just did a simple Google search, and you can see that the mathematical modeling of cancer cell invasion of tissue. And I don't know if I can show the text of this paper because of copyright or not, but if you just search this on the university server, you have access to this paper, and you can see that it basically boils down to a differential equation that models the cancerous cell invasion of a tissue. So that's a dynamical system again. Something is changing with time. Let's go back to here. Another example would be during these days that we have the pandemic. So the spread of the disease in a population, that's also a dynamical system, that spread of a disease in a population. So we are hearing a lot about this these days, that the curve is going up, it's just going down, it's just flat, the curve is flattening, and they say that okay, during the next week, this place is going to be bad, this place, the number of diseases is going to go down or go up. All of those predictions are based on mathematical models again, that they are basically differential equations, and they fall into this category that they are dynamical systems or growth in a population. And you can just come up with numerous examples of dynamical systems. So you can see that it's a very, very, very wide topic, and you can basically, if you enter this field, you can pick up an area that just suits your interest more. If you are interested in, for example, biology, there are dynamical systems in biology that you can study. Or if you are interested, in vibration, vibration is a perfect example of dynamical system in mechanics. And all sort of these examples. So if you are interested in the math, in the behaviors, in these sort of analysis, you can find this differential equation in very wide range of topics. So now we want to just go back again to our mechanical system. So that was a very broad definition of a dynamical system. For a mechanical system, a good example for a dynamical system, well, all the problems that we have solved so far, they are dynamical systems, but there is one special category of them that is more interesting, and that's kind of like a study of oscillatory motion. So a dynamical system, we said that the property changes with time. That change with time might be something like this, something kind of like monotonic behavior. So this is a property, for example, this is the time. So this property changes with time, goes here and then goes here. Or you can just have something like this, for example, that goes from here to here and done. It's not monotonic anymore because it's increasing and decreasing, but the idea is that you don't see a lot of oscillation here. Whereas in vibration, we are very interested in studying the motion of a system that is oscillatory. So the motion goes back and forth between, let's say, different positions, and that's what we mean by kind of like separating vibration from dynamical system. All the vibrational systems are dynamical systems, but a distinct property of them, feature of them, is that they're gonna have a kind of like an oscillatory behavior in their for example, in the position of a particle that is attached to a spring and going back and forth. So again, this would be a property, and this would be time. So this is the kind of like this is a topic for vibration, and you're going to be studying this extensively in a mechanical vibration course. I don't remember the course number, but that's basically the name of the course. So let's have an example for this oscillatory behavior, oscillatory oscillatory change in that property, which here that property would be a position of a particle for us. So let's say, for example, we have a spring mass system here. So this is M, this is K. So the mass is just attached to this spring, and the spring, let's say, is just at rest here. And we want to kind of like derive the governing equation of motion for this system using the stuff that we have had so far, mainly the Newton's equation, but we want to derive the equation for the motion of particle at all times, not just at one particular time. So if this is the rest position for the spring, so this is the rest position for this particle here, for this mass here. So let's assume that, for example, this mass has moved to somewhere to here, to the right side. The spring is stretched here, and then draw the free body diagram for the mass and see what do we get for the governing equation of motion. So let's say that, for example, this is our coordinate system. This is x and this is y. So y is useless here because we are assuming that the motion is just 1D. We are just going back and forth along the x-axis. But let's say this is our coordinate system. So if the particle if the spring is stretched, and let's say the particle is at here, so and again this is k. So this distance is x right now. So this is x, because we consider the origin of x-axis here at the rest position. So if I want to draw the free body diagram for this system, it would be something like this. So we have this mass here, we have the force of spring here, which would be k times x, and it would be in the leftward direction because the spring is stretched. It wants to go back to its initial rest position, so the force on the mass would be in this direction. And we don't draw the forces in the y direction because the particle is not moving in the y direction. In the y direction, basically, we're going to have n, the reaction of the surface, and also mg, the force of gravity, which they cancel out each other. We don't have any motion in the y direction. So this is the only force that is acting on this particle. So we are going to have minus kx in the I direction is equal to, that's sum of all the forces. It's just we have one force here. It's equal to m a x in the I direction. And we can just drop the I vector here because everything is just 1D. And ax would be the second derivative of position with respect to time. So this would be minus k times x is equal to m d2x over dt2, or mx double dot. So if we bring this term to the other side of the equation, we get m x double dot plus kx is equal to 0. And this equation, again, this is true at all times. So basically, I can write down this like this: m x double dot of t at any time plus k x at t equal to 0. And this is what we mean by the governing equation of motion. This equation is true for the motion of this particle at all times. And you might say that, what if we assume that this, instead of the spring being stretched, what if it was compressed? We should again get the same equation, because we are claiming that this equation governs the motion of this particle at all times. So you can imagine when the spring is stretched, when the mass goes to the left side of the rest position, the spring is compressed over there, and this equation again should be true. So let's see if this equation again is true if the spring is compressed. So I'm assuming that here, so this would be, let's say, our mass, and the spring is stretched, and this is, for example, the initial rest position. So here, this is the position of the particle, and basically here is just the x. Remember, this was the x-axis, and this was the useless y-axis here. So if I want to draw the free body diagram here for this particle, so it would be something like this. Again, m, and in the x direction, we only have one force here, so which is the spring force. And the spring force here, because the spring is compressed, it wants to go back to its rest position. So the spring is pushing this mass to the right. It wants to go back to the rest position. So what can I say about this magnitude? Can I say that it is kx? Well, here, because this is the origin for x is a negative number here. So basically, if we say kx, so for example, x here is just minus 1 meter, minus half a meter. X is a negative number, and we want this force to be in the right direction, in the rightward direction. So if I put kx, that's not right actually. So it would be a force in the leftward direction, because now x is a negative quantity. So in order to account for that, I have to just say minus kx, or k times minus x. And again here, if I write down the equation, so it would be minus kx in the I direction. The force is rightward, so, and the value of the force is just minus kx. Basically, this is positive for the rightward direction. Is equal to ma, and a here is just x double dot in the I direction. If we drop the vector notation and bring this term to the other side of the equation, we get mx double dot plus kx is equal to 0. So you can see that we got the same equation. So this equation is true for this particle at any place, any time, as it is oscillating around this rest position. So for this equation, this is a second order linear differential equation. So this is second order because we have the second derivative. So second order. It is linear. The equation is linear because we don't have anything such as, for example, x times x double dot or x squared, the function times itself. We don't have anything like that, or x double dot, or sine x. These are all the terms that, for example, make an equation nonlinear. But here the unknown function, which is x, here is just multiplied. Its second derivative is multiplied by a constant, and here is the function itself is multiplied by a k constant. So because we don't have any of these terms, the equation is linear. And it's an ordinary differential equation. So second order linear ordinary differential equation. And I'm not going to solve this equation, even though we had a similar equation for a motion of a particle under central force, and we solve it over there. But I don't want to get into solving this analytically. So we can solve this analytically because this is a linear equation and a simple equation. We can solve it analytically. We can solve every equation numerically. So numerical solution also could be applied to solve this equation. And because you are going to study this extensively in mechanical vibration, basically 80% of the course or 100% of the course would be about this equation and a little more extension of it. I'm not going to get into solving this analytically. Instead, I want to just solve this very quickly numerically using MATLAB, so that I can just show you some of the features of such system, of a vibrational system. So let's solve this equation with MATLAB. So we have, let's say, mx double dot plus kx equal to 0. And let's say, for example, k is 100 Newton per meter and m is, for example, 4 kilogram. And basically let's say we stretch the spring to 0.1 meter and then leave the system to oscillate. So I would say that x at t equal to 0 is equal to 0.1 meter. X dot, or velocity, at t equals 0. So this is again t equal to 0. It's equal to 0. So I'm not going to give any initial velocity to this mass. Basically, I'm just stretching this spring. So the spring is at rest. I bring the mass to the right by 0.1 meter and then just leave the mass. So the mass is going to go back to the rest position, but at that rest position, the mass has so at that rest position, there is no force acting on the mass because the force of a spring would be 0 at rest, but the mass has a kinetic energy, so it tends to go further beyond the rest point. And once it goes back here, the kinetic energy turns into potential energy into a spring, and then just again goes to some point that just it stops. All the kinetic energy is turned to potential energy in that spring at that point the spring, because the spring is compressed, the spring is going to push the mass to the rightward direction. And because here we are assuming that there is no friction, there is no energy dissipation, the mass is going to just oscillate about the rest position forever. So our goal here is that to see that oscillation for this system with this initial condition in MATLAB. So in order to solve this in MATLAB numerically using ODE45, which hopefully you are all familiar with, but if you are not, it's just nothing difficult about that. We are going to learn about it here. In order to write the equation, to solve the equation with MATLAB ODE45, you have to turn the equation into first order equation. Here we have a second order equation. We have to turn this into two first order equation. The motor is passing by here. We have to turn this equation to two first order equations, and then we can solve it using ODE45. So that's basically the key using MATLAB to solve differential equation numerically. We have to turn them, let's say we have a fifth order differential equation here. We have to turn it into 5 first order differential equation, and then we can solve it with MATLAB. So how can we turn this into 2 first order equation? Basically, we have to take this into a state space, and we have to do a change of variable here. So I would say that if you consider x as x1, that's the first variable, and x dot as x2, so these are the 2 variables. I want to get 2 differential equations on these 2 variables. If I consider this change of variable, I can rewrite this equation as, the first equation that I can write down here is that x dot, x1 dot, is equal to x2. Because x1 dot is equal to x dot and x dot is equal to x2. So this is the first equation. The second equation here, x2 dot, we have to use this equation that we have to come up with the right hand side of this equation. So x2 dot would be x double dot. So we go back to this equation, put x double dot in one side of the equation and bring everything else to the other side of the equation. So basically here, I would say I keep x double dot here, bring this term over here, and then divide both sides by m. So this would be 1 over m times minus kx. Once you isolate this term, the x double dot term, basically you can write down this here, because x2 double dot, as we said, is equal to x double dot. So this would be 1 over m times minus k x, and we know that x is equal to x1. So now we have 2 first order equation on x1 and x2, and we know what x1 and x2 represent. x1 represent the position, x2 represent the velocity. So now let's go to MATLAB and solve this equation, and let's just play with the value of these parameters to see how the response would change. So I'll get my keyboard here. add to the keyboard, and here basically I have MATLAB open here, and I'm going to go to the Home tab and just open a new script so that I can write the code for that equation. So this is the equation again, going back here. This is the equation that we are trying to write in MATLAB and solve. So let's first introduce these parameters and then write down the function for these two equations. So let me go to here. So here I would say clear all to start, close all, and CLC. So the spring constant was 100, so I would say K is equal to 100. The mass of the particle was 4 kilograms, so I would say M is equal to 4 kilograms. And a good practice is just to comment here to say that what the units of these systems are, these parameters are. But because here we have a simple equation, it's not necessary here. So K is equal to 100, M is equal to 4, and now we want to solve this. So I would go here and say that T and X here, so it would be actually T and X is going to be ODE 45. Let's say name the function oscillator, for example, add oscillator, the interval in which we want to solve the equation, the time interval. Let's say you want to solve that equation for time 0 to time 20 seconds or 0 to 50 seconds. So we specify an interval over there, and also the initial conditions I see over here. And now I have to go back and define these IC, interval, and also the function. So for the initial condition, I would say that IC is equal to, remember that the initial condition on x1 was the initial position, and we said that we stretched the spring for 0.1 meter. And the initial condition on x2 was the initial condition on velocity, which was 0 initially. So that's the initial velocity. For interval, I would say, let's solve this for 0 to 20 seconds. We can change that later on, for example. So 0 to 20 seconds. So these are the initial conditions and intervals. Let's save this. So let's go here and just make a folder here, dynamics, and call this, for example, 1 DOF, 1 degree of freedom system. So that's the name of the code. And also I have to write another script here to define this function, the oscillator function. So I would open another tab and would say, for example, function. You can put any name here. I usually put DXX is equal to oscillator. So this is the name of the function that we were using in the other code to call on this function. So oscillator of T and X. So now we have to write down the first equation. So dxx1. So we use a vector matrix here to represent the right hand side of the equation. So let me go back here. So here I want to tell MATLAB that the first equation, the right hand side of the first equation, x1 dot basically is equal to x2, and x2 dot is basically 1 over m times minus k x1. So I have to write down the right hand side of this equation. Once we have all the variables here as x1 dot, x2 dot, x3 dot, whatever we have here, we can write down the right hand side of the equation for MATLAB. So let me go here. So this is basically x, because I'm using this name, you can use any name here. For example, you can use BU, whatever, MESAM, whatever. You can use your name here, doesn't matter. I usually use just dxx, and once you define that name over here, you have to say, okay, dx11, that's going to be the first row and first column. So this is equal to x2, and then we have the second row and first column. So dxx21, this is equal to 1 over m times minus k times x1. And that's basically our function. So let me put a semicolon here. So when I say a vector, so here if I go back again here, I can write down these two equations. I can say that this is, get my pad again, so this is basically, let's call this vector x dot, which is going to be x1 dot, x2 dot, this is going to be x2, 1 over m minus k x1. So this is a vector. This is what I mean by dxx11. That's the first component. Here, this would be second row, the first column. You have to write down this in a vector format and then introduce it to MATLAB. So let me go back to my keyboard here. And now the only thing that we need to do is to also define these parameters in the function. So in order to do that, I define m and k as a global parameter. So that global m and k. So it would be global between my code here and also the function. So global m and k. So let's save the function here. So, and we have to same the function with its name. Otherwise MATLAB wouldn't recognize it. And we have to same it within the same folder. So hopefully you are familiar with this. But if not, this is basically how it is done. You have to save your code and also your function within the same folder, and your function should have the same name as you gave to it in your code. Here we are calling on function oscillator, and the name of this function should be oscillator here, and also for the name of the file. So that here MATLAB just goes one line by one line, and when it reaches this point, it realizes that we are calling on this function and would go and just run this code. So basically this is all we need to solve that equation. And right now if I run this, we should be able to solve this. So here you can see that we are getting the x vector, which is going to have two columns here. The first column is just the position. The second column is the velocity. This is x1, this is x2. So if I go to the plus tab, I can plot this. For example, you can see that we have a oscillatory motion here, that it started actually at point 1 because we gave that initial condition to the system, and there was no initial velocity. So you can see that the tangent to the curve at 0 times 0 is equal to 0. That's the initial velocity. Or we can also draw the velocity here. So the velocity starts from 0 because we didn't give it an initial velocity, and then once we leave the mass to move, it is going to, because we have stretched the spring, it is going to go to the leftward direction. That's why the velocity at the beginning is negative, and then after it reaches a point, it's going to go back in the right direction. So actually, let's plot these columns here, x for example here in our code, because we want to do some comparison here. So let me go here and say that figure and plot t. We also had the time vector over there. So these are the positions. At what times we have to open the time vector. So these are the times that we have the velocity and the position of the particle at. So we have the t, x, and velocity. So I want to draw the graph for the position of the particle. So I would say plot t, x, and we want to have the first column, which is the position. So all the rows and the first column. This is how we introduce this. And let's use also a bigger line width for the graph. So line width equal to 3. And let's put grid on. X label would be time in second. Y label would be x in meter. So let's adjust the font size for the labels. So set GCA font size. Let's go with 24. So I think that's all we need. So now if I run this code, or actually to bring the code here into the picture so that you guys can see it also, I wouldn't need to move it every time that I make a plot. Let me bring this line of code here. So this would adjust the position of the figure into this window so that you can see it. I adjusted this before I starting this video, so hopefully this will make the graph in this window here. Yeah, now you can see the position of the particle as a function of time. And as I said here, the tangent to this point should be horizontal because we don't have any initial velocity for the particle. And now for this system, you can change everything so that you can see how the response would change. The first thing that I want to change here, let's just change the y limit here so that we can see a little above this. So I would go here and say that, so let's call this max of x, which would be equal to maximum of absolute value of x and 1, the first column. And then I would say y limit would be, let's say, minus 1.1 times max x and 1.1 times max x. So if I run this, okay, now we can see just a little bit below and also above, so that's good. Let's change this to, so basically I said that choose the maximum value of x and adjust the y limit of this figure to minus 1.2 times that maximum and also 1.2 times that maximum so that we can have a better picture of the graph. And you can see here the oscillation is between two fixed points on the right side and also the left side. Because we don't have any energy dissipation, we have the conservation of energy. Basically, the particle goes from a certain location at the right side at the initial position that we gave to it, to the certain position on the left side of the equilibrium point, and then oscillates between those two points back and forth. So let's see how this changed. For example, if we give it an initial velocity. So instead of initial displacement, so I would make that 0, and here I would, for example, give it an initial velocity of 1 meter, for example, 1 meter per second. So let's run this. Now, as we expect, the position starts from 0. That's the initial position of the particle, and you can see that now the tangent to this curve is not horizontal anymore. That means that we have an initial velocity, and basically this is how the particle can oscillate, and we can give it an initial velocity and also initial displacement at the same time. So for example, 0.1 meter initial displacement and 1 meter per second initial velocity. So if I run this, we get something like this. The position starts at 0.1 and the tangent to the curve is not horizontal anymore because we have an initial velocity. So you can play with these values to see how that change, or you can also change this time interval. Let's say you want to study the motion from 0 to 50 seconds. So if I run this, it should go for more number of cycles here. This is the 50 seconds. So this is how you solve the governing equation of motion for a simple mass spring system in MATLAB. And now let's consider a little bit of energy dissipation. So let's say that this particle that we had. So let me go to the writing that we had. Let's say that there is no friction between this particle and the surface, but we have air here in the system, and the particle faces a resistance from air to just move here, just basically loses its energy by moving through air. And again, this is something that you will extensively study in mechanical vibration. But to just give you an intuition here, the force that the existence of air, the air molecule would exert on this on the mass, how that force would be. So if the particle is just going to the right, the force that the air resistance exerts on the particle would be in the leftward direction because it wants to resist the motion. So if the particle is going to the right, the force of air would be in the leftward direction. And if the particle is going to the left, the force from air would be in the rightward direction. So that's for the direction of the force that air molecule exerts. Basically, they are in the opposite direction of velocity. Not for position. Here you can see that the position of the particle is in the negative side of x-axis, but if it is going to the right side, the force that air molecules exerts on this particle would be in the leftward direction. So the direction of the force adjusts itself by the direction of velocity. It would be always in the opposite direction of velocity. So that's for its direction. For its magnitude, and a good intuition for this would be, let's say you are in a car and, for example, you bring your hand out of the window or the sunroof, and let's say the car is just going 40 miles an hour. You feel some force on your hand. If the car increases its velocity, let's say it's going by 60 miles an hour, you feel more resistance, more force that the air exerts on your hand. So you can say that the force that the air molecules exerts on the mass depends on the velocity of the mass. And basically, again, you will derive an equation for this in mechanical vibration that for Newtonian fluid, you can show that the force that air resistance causes on the mass would be proportional to the velocity. So if I go here, F of air molecules would be proportional to velocity, and we can turn the proportionality into an equality here with a constant here, which we call that constant c, and this would be c times x dot. And its direction would be basically, so let's say that again we have the mass that is moving to the right here. If it is moving to the right, x dot is positive, so the force would be negative on the leftward direction. So we should put a minus here to show that for the direction of the force. So if we consider, aside from force of a spring, if we add this term also, if we consider this force on the free body diagram and add this term into the equation, we come up with something like this: mx double dot plus kx plus cx dot equal to 0. So this was minus cx dot on the other side. That was the force that the air molecule they were exerting on the mass. And once we bring it to the other side of the equation, to the side that we have the acceleration, it will be a positive term. So now this is the differential equation for a spring damper mass oscillator. So this energy dissipation, we say that causes damping in the system. And this C is basically damping coefficient. So now let's just go into our equation. We are solving that. Let's just add this term. Just pick a value for C. Let's say, for example, C is equal to 1, or we can actually change it. See how the response would change if C, for example, changes from 1 to 10. And we should expect that if we don't have this energy dissipation, as we saw, the oscillation goes forever because there is no energy dissipation in the system. But once we add this system, we expect that the oscillation, the amplitude of oscillation, gets smaller and smaller as time passes because the energy is dissipated in the system. So let's go to our code, and basically if I go up here, so I have to add the minus c x dot term here, and x dot is equal to x2, so that would be minus c x2. So that's basically adding damping energy dissipation into the system. So if I go here, go to the function and say that this is minus c, put the pad aside again, minus c times x2. I have to also define c as a global parameter, and then go back here and have c as a global parameter here, and let's say, not kc, k and c. Let's actually solve this equation for two values of c and see what we get. So this is the first figure. For example, let's make this a subplot here. So subplot. Let's say we want to have two plots side by side, so it would be just one row, two columns. So one row, two columns, and this is the first plot. And for the second plot, so here I define, for example, c as 1. And then for the second plot, I change the value of c to 5, for example. And I want to solve this equation again, so I will bring this down here. And let's call this t2, x2. We want to solve the oscillator function again here. Then interval and initial conditions are the same. So this is it. And then let me copy this here. For the second plot, I can actually bring this higher here so that we can have everything neat here. So let me bring this C here. Okay, so this is C, the first value for C, solving the equation, the second value for C, and solving the equation again. We are storing the results for the first equation as t and x, the second equation as t2 and x2, and let's draw the second subplot here. So this would be 2, and this would be 2, t2, and this would be 2. Also, let's put a label for a legend, for example, or title for this. So title this is C equal to 5, and this would be C equal to 1. So let's solve this. So what do we expect? So I said that this shows how much energy dissipation we have in the system. This is the damping coefficient. So we kind of expect as damping increases, let's say, for example, instead of air, you are moving through water, you're going to experience more resistance. Your spring mass is moving through water. So that causes more resistance. That means more damping, and that manifests itself in terms of a larger damping coefficient. So we expect that the oscillation in this case to be damped faster compared to this case. So let's run this, see what we get. Oops, we got an error here. So I should say for the, oh, we copied this twice, so yes, here. Oops. We got the results, but we are also getting an error, I think. Oh, title. Oh, I wrote it, so this is title C5, and here would be title C equal to 1. There we go. So this is where, first of all, you can see that the oscillation is just damping out. The oscillation doesn't go forever. Maybe it's better to just compare when C is equal to 0 and C is not equal to 0, but you get the idea. I will do that comparison also. So here you can see that as we have more damping, here after few oscillation, the response just dies out and goes to 0. And that makes sense. The system is losing energy. But here, because we have less energy dissipation, we have the oscillation up to 20, 30, maybe 40 seconds. The oscillation continues and goes on. But here the oscillation damps out very quickly. So let's run that. Let's make this C1 equal to 0, for example, and C2 equal to 1 now. So this is 0 and this is 1. So this would be the case when we don't have energy dissipation. The oscillation just goes on forever. And when we have energy dissipation, the oscillation damps out. And again, in the mechanical vibration course, you will derive the analytical solution for this case when you have damping. The governing equation of motion that we had over there when we added the damping term. So if I go down here, again, you can solve this equation analytically, but here we want to do everything numerically. So let's do another case here. For example, let's just increase the value of C very dramatically, and you will see that there will be no oscillation. The oscillation just damps out in terms of an exponential function, not in terms of a harmonic function. By the way, this curve here that you can see that the oscillation amplitude is just decreasing, this is a kind of like exponential decay here that you have. And again, you will derive the expression for this, the analytical expression. For the line that connects all the peaks here to each other, you will see that this would be an exponential function. So let's, for example, here consider case C equal to 100. And C equal to 1, for example. So C 100, and this is 1. So you can see that there is no oscillation anymore. It's just that the response just damps out. Just goes up and then damps out. So that's when you have a kind of like, they call it over-damped system. So that's one interesting thing that we can do. This would be kind of like the theme for all the vibration course that you're going to have. First, you will start with a system that is just, there is no energy dissipation in that system. Everything, the equation is conservative. and then you just go and add complexity to the equation. First, you add the damping. Another thing that you can do is just to apply an external force on your system and see how the response would change when you have an external force. So let's go back here. Let's say that we have, and let's throw out the damping term, for example, here. Let's say that we have an oscillator here, M0, 0, K, and it is at rest. We don't give an initial velocity or initial displacement to the particle, but there is a force that is acting on the particle. Let's say you have a force, F of t, which is, for example, F, a constant, times sine omega t. So this would be called forced vibration. This force causes this mass to oscillate, and we can just add this term into the equation. So the equation in the presence of this term would be mx double dot plus kx is equal to F sine omega t. And we can change these two variables that we have, F and omega, to see how the response, the x, would change. Why did I consider F sine omega t? You can basically consider any force, any time function, let's say t plus 3, or I don't know, a constant force, which is not that interesting, for example, minus 1, or an exponential force, let's say e minus t. So you are free to just consider any time function that you want. The reason that the first force that I considered here was the sinusoidal force is that basically you can use Fourier analysis to write functions in terms of sine and cosine, and that's why I considered this term here. And again, in the mechanical vibration course that you have, this would be kind of like the first external force that you would consider for your spring mass system, and see how this force, the parameter of this force, which is its amplitude F and also its frequency omega, would affect the response of the system. So that's why I just consider F sine omega t. It just gives us an interesting result, and also we can use sine and cosine terms to represent other time functions using Fourier series, and that's why we are considering this. So let's go back to the MATLAB code. So let's for example, let's just get rid of damping, C equal to 0. For two cases, C equal to 0. Let's add the force term here. So this here we would have plus F times sine omega times t. So I should also define F and omega here as global variables. Go back here and do the same thing here. So F and omega. Let's give a value to these quantities. So because we are having two subplots, let's see how the response would change if we increase, for example, the value of F. So let's solve at the beginning with F equal to 1, for example, and omega equal to 3, for example. And in the second case here, let's solve with F equal to, let's say, 4, and same omega equal to 3. So basically I'm going to solve again the same equation once with one time with omega with F equal to 1, omega equal to 3, the second time with F equal to 4, keeping the omegas same. And here I would say that this would be F equal to 1, and here this would be F equal to 4, for example. So let's run this, and this is what we get basically. So you can see here, first of all, notice that we had, let's see if I cancel out the initial velocity and initial displacement now. So let's put 0 and 0 here. No initial velocity, no initial displacement, but because we have force vibration, the mass is going to move anyway. So here is the difference. So again, we have the oscillatory motion here, and you can see that when we have a larger force, the amplitude of vibration, here the force amplitude is just 4 times more than this case, and the amplitude of vibration is 4 times larger than this case. So there is a linear relationship in this case between the amplitude of the force and also the response, the amplitude of x. So that's the first interesting thing that we can do with this. Another interesting thing that we can do with this is to keep f constant and change omega. You might be able to see where I'm going with this. So let's say f equal to 4 here, omega equal to 3, and here let's put omega equal to 1 and also omega equal to 4. And here also I want to have the same y limit for both graphs so that we can compare them. So let's say that this is max. Let's bring this equation here. Bring this equation here. So this is the maximum that we use for, let's call this max 2. And let's call this max is equal to max of the maximum of these two values that we had. So max 2. Let's call this max 0, for example. So we want to have the same y label for both subplots so that we can compare them better. So here and also here. So omega is equal to, so omega is equal to 4 here, and omega is equal to 1 here, backslash omega. So if we run this, so let's see what we got. So here you can see that by changing omega, not by changing the frequency of force, not the amplitude of the force, the maximum response that we got for the amplitude of vibration, the position of the particle, it changed dramatically. Here, a little below 0.2, and here almost 0.4 for the maximum of displacement here. And this is something interesting because we didn't change the amplitude of the force, as I said. And you can see here that there is no linear relationship between how much we increased omega, the frequency of the force, and how much increase we got in the amplitude of the displacement. So that's the comparison between omega 1 and omega 4. And basically here we can do something interesting. So let's go, for example, so let's just comment this out. So let's start from 1 and go, for example, to 7. So omega equal to 1, omega here omega 1, omega 2. So the left graph would be for omega 1, the right graph would be for omega 2. So you can see that here, as we are going from omega 1 to omega 2, the amplitude is increasing. Let's now keep this one, bring it here, and then draw omega equal to 3 on this side. So let's have omega 2 and omega 3 here. Again, as we are going from omega equal 2 to omega equal to 3, we have an increase in the amplitude. Let's go from 3 to 4. 3 to 4. Again, we have an increase in the amplitude. We are going from 3 to 4. So now let's go from 4 to 5. this is the interesting point that I was looking to see here. So now here you can see the amplitude for 5 is much larger than for 4. But another interesting thing for here is that the amplitude is constantly increasing. So here we are just going up to 20, and it seems that if I increase the interval that I'm solving the differential equation for, this response would just keep increasing. So let's change the interval. So here it was going from up to 20, and we were solving up to 50 seconds. Let's solve it up to, let's say, 100 seconds. You can see that the increase in the amplitude response just goes on and on, never stops. And this phenomenon that happened here just has a name. We call it resonance, which I think you are already familiar with. So you can see that here, as we are changing the frequency of the external force, you can get this kind of like interesting behavior in the response of the system. And again, you would see why the response is just going here to infinity. Basically, if you just continue increasing the time interval, this response just keep increasing and basically goes to infinity. If you solve this analytically, again in the mechanical vibration course, you see why this happens. So this phenomenon, it's just, as I said, is called resonance, and it happens when, so this value of 5, so you might say, why did it happen at omega equal to 5? So again, when you solve that equation analytically, you will see that the frequency associated with the resonance would be equal to a square root of k over m. So let me go to the path. So you would see that omega equal to square root of k over m. They call this natural frequency of the system. And the meaning of that is that, well, two things. First, when we say that this is natural frequency, when we had the vibration of the mass due to initial displacement and initial velocity without any external force, if we calculate the time interval between the two peaks, so let's say we had, this was the oscillation that we had when we were giving just an initial velocity and initial displacement to the system, no external force. If we measure this duration, the time that it takes between two peaks, and call this Tn, this would be natural period of the system, and it would be basically Tn would be 2 pi over omega n. And that's why we did call this omega n natural frequency. The frequency of free vibration for this, not forced vibration. The free vibration for this system would be would be equal to this ratio, the square root of k over m, which depends only on the internal property of the system, k and m. And if I substitute the value of k and m here, so it was 100 over 4, which this would be 125, square root of 25, that's 5. And that's why we saw the resonance at omega n equal to 5. So maybe just better to say it in an organized way. So omega n, the natural frequency, that means when we have free vibration, the frequency of that free vibration is omega n. Or another easier way to think about it is that the natural period, which is 2 pi over omega n, the time that it takes between two peaks is equal to natural period, Tn, 2 pi omega n. That's the first meaning of this. The second thing that we get from this omega n is that if we have an external excitation, if we have a force on the system, and the frequency of that force is equal to the natural frequency, we are going to have resonance. So we saw that when we were changing omega from 1 to 2 to 3 to 4, the amplitude was increasing, but at omega n equal to 5, exactly the natural frequency, the amplitude goes to infinity. So that's the meaning of the natural frequency, this ratio, and also the information that we can get from it, that the system should never be, for example, if you don't want to break the system, you shouldn't allow a harmonic force on the system that is frequency is equal to the natural frequency of the system, or it is close to it. We saw that as we are getting close to omega n equal to 5, the response it gets larger and larger. And actually, if we pass 5, again, we are going to have when we pass 5, we're going to have a decrease in the amplitude. So let's say this is 5 and this is 6. Once we pass that resonance, you can see that the response again is smaller. So as we are approaching this 5, the natural resonance, we are going to have the increase in the amplitude that goes to infinity. So here the next step for us would be, for example, we consider the damping, we consider the force, external force on the system. Now let's just consider both of them together. So let's say, for example, here, consider again 5 and 6 and just give same damping here, C equal to 1. And let's solve this. So we are introducing a little bit of energy dissipation in the system. And you can see that that little energy dissipation in the system bounded the response of the system. So we don't have the response going to infinity, just increasing linearly as time passes. The system response is bounded just because of that damping. So this would be forced vibration of a damped system. The other thing that we can do here, for example, is let's get an important curve for this system, which is called frequency response curve. So we saw that as we are changing the frequency omega, the amplitude was changing. The amplitude depended heavily on omega, the frequency of the external force. So now let's just, for example, consider a for loop and just sweep the omega between a certain value up to a certain value and see how the maximum amplitude would change. So let me put the pad aside and get the keyboard. So basically what I want to do, let's just copy this code here. So we want to do a frequency sweep. So let's put damping equal to 0, for example, F4. And omega here, I would say that 4 II equal to 1 to 100. Let's say omega is equal to II over 10. So basically we want to sweep omega from when II is equal to 1, that would be 1 over 10. We want to sweep omega from 1 over 10 to 10. When II is equal to 100, omega would be 10. And we want to see how the amplitude would change. So here we want to solve this equation and store. So let's just store the value of omega at each step. So omega record, for example, omega rec II would be equal to omega. So I'm just storing this value because I want to plot the maximum of amplitude against this omega later on. We solve the equation and I want to record the maximum response in a vector. So let's say x rec II is equal to max absolute value of x, the first column, which is the position. Oops. Then that's it basically, that's end. So I want to just solve this equation over and over for different value of omega. So let's get rid of these things. And here I want to just have one plot and it would be omega rec over against x rec. So this would be omega in radian per second, and this would be amplitude x in meter. So that's for position. We don't need the y limit here. We don't need this graph here. Okay, and just let's add another line of code here, fprintf, to just see, because this loop is gonna go for 100 times. Let's just have a index for that to see where in the loop we are. So fprintf, I would say so this would just, once we are at the first value of the loop, I equal to 1, just prints out 1 for us, and then 2, and then 3. We see how quick or how slow the loop is going. So now I think we can run this. So C omega is over there. Let's run this. Okay, and call this frequency sweep, for example. So if I go to MATLAB here, you should see 1, 2, 3, 4, waiting for it. Oops. Oh, I think I made a mistake here. So let's run this now. Okay, so 1, 2. So that shows the index of the loop as we go through the loop. So we are sweeping omega and see how the maximum response will change. The maximum of the amplitude for the position. Okay, now you can see that resonance here at omega equal to 5, exactly at omega equal to 5. And as we pass that omega, again the amplitude would decrease. So that's something interesting. This curve is called frequency response curve. Basically shows this maximum of amplitude versus omega, not time anymore. And now we can do a couple of interesting things. We can, for example, add damping or add nonlinear terms actually, which is the next step, again, next logical step in studying this system. So in your mechanical vibration course, you are going to be studying just that simple equation, the oscillator. Let me write down here. So this term that we had, this equation that we had in its general format. So you will start with the free vibration, which is basically mx double dot plus kx equal to 0. Free vibration and undamped insect. If you add damping, you add damping here. So add damping, you get mx double dot plus kx plus, let's write down cx dot first. Cx dot plus kx equal to 0. And the next step is to just add the forcing here. So not free vibration, but forced vibration, which would be mx double dot plus cx dot plus kx is equal to f sine omega t. So these are the steps that you take in the mechanical vibration course to progress from this system to a little more general case that you have damping and also force. Then the next logical step would be to add nonlinearity into the system. How would you add nonlinearity in the system? So let's go to the sprint that we had. So, and the reason that I'm writing down this pattern is that this is basically several courses that are offered in vibration and dynamical systems in the mechanical department basically go through the logical steps that we had like this. I will explain further as we go on. So let's here, let's say that, let's go back to the spring damper system here, and we basically here assume that spring mass system here. We basically assume that the force of the spring is just proportional, it's just linear in x, so basically minus kx, if you want to say correctly. Or if I have the force of a spring here, its absolute value, it would be a line here. And that's basically why we have a linear representation, linear mathematical model for the spring. But not all springs just behave this way. So this curve, this equation is basically obtained by, let's say, assuming by searching this spring for several values. Say you have a table that just records x and force. So you just gave it 0.1, you get, let's say, 1 Newton. You get 0.2, you get 2 Newton. 0.3, 3 Newton. And you draw all those points here, and you get this curve. And you say, okay, this curve is pretty linear, so let's say that the force is some constant times the value of x. Here it would be F equal to 1 over 10 times x. That's the constant of the spring. But let's say you have a spring that is just made from a material that once you do this, the x and f table, you get something like this. Let me use another color. Let's say the first point is here, the second point is here, the third point is here, then it is here, then it is here, then it is here. So you can see that this is not a line anymore. The spring force is a kind of like a non-linear, it's a curve, it's a nonlinear function. It's not a linear function. So here you can say, for example, f of s, its magnitude is some constant times x plus a constant times, for example, x cube. You have a nonlinear term here. And if you consider this model for the spring force, which, for example, a material like rubber exhibit this behavior, or even metallic springs, if you have very large deflection, they become nonlinear. They don't follow this path. So even for the nonlinear spring, it wouldn't go all the way to infinity. At some point, it just starts to diverge from this linear behavior. If you want to consider this behavior into the equation of motion, what do you get? So we will get m x double dot plus kx plus alpha x cube is equal to 0. So now you have a nonlinear ODE. Why nonlinear? Because you have the unknown function multiplied by itself. You have actually power of 3 of the unknown function. So this is a nonlinear ODE. And you can have all sort of equations for the force here. Just I consider x cubed. You can have x squared, for example. You can have x squared x cubed together, or everything. Basically, if you have a nonlinear spring, that makes the equation of motion, governing equation of motion, a nonlinear equation. And solving this nonlinear equation, that would be topic of another course, which would be nonlinear equations, or nonlinear vibration, nonlinear oscillations. Or sometimes in a more general case, they call it nonlinear dynamics. So nonlinear, which again, these are courses that are offered in the department. So nonlinear vibration or nonlinear oscillation, these are both same thing. Usually they refer to a dynamical system, which is a vibratory, oscillatory mechanical system. Or in general case, you have a nonlinear dynamical system. All those phenomena that we said that they are dynamical system, nonlinear dynamics. So dynamics. Let's say the weather, or just the spread of cancerous cell in a body, stuff like that. They under certain circumstances, they can be modeled with nonlinear equations, and that would be a topic of that would be a subject that is studied in a general course that is nonlinear dynamics. So for nonlinear dynamics course, again, when you take a course in that, you're going to have the same kind of like progression that we had. First, you're going to have the free vibration of this system. Then you're going to add damping, for example, so free vibration. And then add damping here. So it would be something like this, mx double dot plus kx plus, let's say, beta x squared is equal to, or forgot the damping term, plus cx dot is equal to 0. Or sometimes in nonlinear vibration, you have a damping force that is nonlinear. So you have an equation that the spring is linear, actually, kx, but the damping term, for example, is just cx dot, let's say, x dot squared here. So that's your damping term. So start from free vibration, add damping, and you can guess the next logical step here is just forced vibration for nonlinear systems. So mx double dot plus kx plus, let's say, alpha x cubed plus a damping term, let's say a linear damping term, is equal to f sine omega t. Or this force could be a nonlinear function of x. That's actually one of the equations that I deal with in my research. So I heavily kind of like deal with this equation, mx double dot plus kx plus cx dot is equal to something like this, a naught plus a1x plus a2x squared plus all the way, let's say, to a9, for example, x to the 9 times a function of time, which is a form of, say, constant, let's say, alpha plus b sine omega t squared. So you can see that this is again a governing equation of system for a linear mass spring system with linear damping, but the force is a nonlinear function of x, actually. And this is basically an equation that I use very much in my research. So that's a progression for this kind of like nonlinear dynamic, nonlinear vibration stuff. Another progress after this, next logical step for this would be if we have, so a better way to say it, that so far we have assumed that all the mass and all the springs in the system are separated from each other. Basically, we have assumed that the mass is rigid and the spring is massless. So spring, rigid mass so far. Even after, if you take these courses, mechanical vibration, nonlinear vibration, let's say you study with rigid mass and massless springs. But what if you have a system that you don't have a rigid mass, or you have a spring that you cannot ignore its mass? So far we have assumed that the mass of this particle is much larger than the mass of this spring. So we basically ignore the mass of a spring. But if that's not the case, or if the mass is not rigid, then that assumption is not correct anymore. And in that case, if you have a rigid mass or a massless spring, an example for that, another example would be, let's say you have your ruler here, you fix it on one side and just kind of like deflect the other end of it and just let it vibrate. So basically you have a flexible structure that it just goes down and then goes up, oscillate here like a cantilever. So in this system, the mass and the spring, we don't have a rigid mass, we don't have the stiffness is in the structure itself. So the mass and the spring are kind of like distributed in the whole system. They are not concentrated at different points, separate points. So this would be a topic of a course called vibration of continuous systems. So vibration of continuous systems. And basically this is the first time that you kind of like go to the transition from ODE to PDE. So let's say you show the deflection of this ruler, this cantilever, with W, and this is the X. The deflection of W depends on where on the cantilever we are, where on the ruler we are, on the X, and also the time. At each position, the vibration at that point depends on time. And also the deflection or the amplitude depends also on where on the beam we are. So this would be a function of two variables, Wx of t. And basically you get a partial differential equation for it. So it would be a constant, for example, that constant, let's call it EI. You don't, none of these stuff that I'm introducing this, it's going to be questioned on exams or stuff like that. This is just, as I said, for an introduction for you guys. So this would be EI times the fourth derivative of that function W with respect to X plus a constant, which we call it rho A, the second derivative with respect to time equal to 0. So basically a constant times, this is something like the stiffness term, this is something like the acceleration term. But because this is a function of x and t, we have partial derivatives here. And we have a PDE here. So in such a course for vibration of continuous system, again, you will start with the free vibration of a continuous system like this. And you have a PDE instead of OD. The next step after this in such a course would be what? Would be adding damping again. So damping. Again, you would have a term that is just proportional for, let's say, derivative with respect to time, c times derivative with respect to time. The next step is just adding force, external force. The next step after that would be adding nonlinearity. If the structure is made of certain material, or if you have a very large amplitude vibration, you have nonlinear terms that will add to this PDE. That would be it for that course, kind of like the progression in such a course. And all these courses that I said, all these kind of like nonlinear vibration of continuous system, when you start to study them, they're going to show interesting behavior similar to what we saw for the resonance of a simple linear system. Much more interesting compared to that single resonance that we had in a linear discrete system, basically. So for a linear discrete system, the only interesting thing that we had was just this resonance. But for nonlinear systems or continuous systems or nonlinear continuous system, you're going to have much more interesting phenomena that you will study if you want to take those courses. So as an example, I can add a simple nonlinearity here to this equation that we had. So let's say there is a alpha equal to 1. And we say that here alpha also define it in the function alpha. So I want to just solve the equation that we had, but have a nonlinear spring. So alpha, and here this would be, we have to bring alpha here. So minus alpha times x to the cube, x1. So we got the frequency response for this, for the linear system when we have a linear spring. And now I am assuming that we have a nonlinear spring. And the spring equation is just k times x and also plus alpha times x squared, which we bring it, when we bring them into the right hand side of equation, they will be negative. And we have to multiply everything by 1 over m. We have no damping, we put c equal to 0, and we want to just do a frequency sweep to see what happens to the amplitude of to the maximum point of the amplitude of vibration when we are sweeping omega. So if I go there, and here basically let's also make the step a little finer here. So let's go with, for example, 60, or here 60. Let's go from omega 2 equal, let's go from omega 2.1 or 2 plus 1 over 60, or let's say 50, to when omega is 100, this would be 2, or that's actually a small. Let's make this 3, for example, and this one, make it 25 maybe, or this one 3.5, sweeping omega from 3.5 to 5.5, or a little more than that. So I'm sweeping omega from 3.5 to 100 over 40, that's 2.5, so it would be 6. So from 3.5 to 6. So let's solve this. Again, let's go to the MATLAB window here. So the code is running. I want to just show you an interesting phenomenon that happens when the system becomes just a slightly nonlinear. We had one simple nonlinear term, small compared to the spring constant. The k was 100 and alpha was 1. So you can see here that that resonance curve that you had, that resonance behavior that you had, the frequency response curve that you had is tilted to the right. And actually here we will see much more interesting stuff if I draw the markers here. And let's get rid of the line here. So line style none. So this is something interesting that you can see here, that let's say you have your oscillatory system and you are operating it at, you are exerting a force on the system with this frequency here, and then you just slightly change the frequency here and you are going to have a jump in the amplitude. So that is something that is very dangerous for many systems. Actually could be beneficial in some cases and also could be very dangerous in some systems. So this jump phenomena that you have here is something that is feature of nonlinear systems, and many more phenomena actually. So you have jump, bifurcations, or chaos, fractals, all those sort of interesting behaviors that I cannot go through all of them right now, but you get the idea. As you get to more complicated system, you get like more interesting behaviors that they actually happen in nature. If you have a vibration, an oscillatory system that is spring is nonlinear, you will see this jump phenomena in this, that you change slightly the frequency of your excitation, your external force, and the amplitude jumps to like 2-3 times more than what it was before. Or the other way around, if you are operating at this frequency and then just increase the frequency a little bit, you have a sudden decrease in the amplitude of the system. So this jump phenomena would be another interesting phenomena for nonlinear systems. And actually here I want to introduce a very good, so there are several good resources to study nonlinear systems, nonlinear vibrations, or in general course general case nonlinear dynamics. But one good resource is just, if you just search nonlinear dynamics, Professor Strogatz here in YouTube, and you get a whole lecture series which is 25 lectures. And basically the only thing that you need to just go through this lecture is just ordinary differential equations. If you have passed that course, you can just go through this whole lecture series, and he will discuss he discusses nonlinear dynamics in general case, not just for mechanical systems, vibratory systems, but for other very interesting phenomenon or examples, nonlinear phenomena that you can see. And actually, one of the videos that he has, I think, for lecture 13, he shows several nonlinear phenomena that happens in nature, and they are very interesting. So I would highly kind of like recommend to at least take a look at this series. If you are interested, then you can just go through this series. Maybe not right now that you are about to enter the exam season, but maybe just during the summer or whenever you have free time and you are interested. As I said, you can go through this course. And one of the examples that he shows that I really like here. So here is just one of the things that I said, that if you have a very large vibration in the system, or suddenly that would be very scary. It's just for an airplane. If you have an airplane, you don't want to have a kind of like sudden change in the amplitude of vibration for the wing, for example, because that would destroy the plane. So these phenomena, they are gonna be they exist in nature in several examples that he show in this course, actually, for even chemical engineering stuff. And they are because of different phenomena, not just because of that jump that I showed you, but you can have chaos, bifurcation, all sort of things that kind of like give you a behavior that is very unexpected. And one of the job of a person who studies these mechanical systems this dynamical system would be kind of like study these phenomena, predict them, and see how, for example, you can avoid them when it is necessary, or how you can take advantage of them. So this is, I think, all I wanted to mention about kind of like the vibration, nonlinear stuff. Another video that is very good, that is very short actually. If you search this channel, Vertasium channel on YouTube, Chaos, they will just explain about chaos phenomenon on nonlinear systems in just 18 minutes, which is very good kind of like example of just getting an idea about what these courses are about, what these people are studying for dynamical systems. And you can just choose for yourself that if this is something that interests you, to just go a little further beyond and just study more on this, or maybe take more courses on this. Or if you just see that, okay, this is not something that is in your interest, or you don't like them, this is good that, you just, for a couple of minutes, less than 20 minutes, maybe spending an hour, you just kind of like discover that, okay, there are such a stuff, they exist, there is such a research field, there are such kind of like studies, but this is not something that I want to do. I want to just go, for example, study fluid mechanics or just something else. So that's why I say I recommend to just kind of like take a look at these videos and just evaluate for yourself to see if this is something good for you or not. So I think with all these things, now we are in a good position to go ahead and study the Euler-Lagrange approach to derive the governing equation of motion for an oscillatory system, or any dynamical system in mechanics for motion of any particles or rigid bodies. So far we have used the Newton approach to derive Newton and Euler equation to derive the governing equation of motion and see how the motion of particle is, but we can use the Euler-Lagrange approach, which is a very powerful method to derive the governing equation of motion for any particle or rigid body in motion, and especially for oscillatory systems. So I think I'm going to take a little bit break, and after that I'm going to be back by kind of like introducing the Lagrange-Euler approach. Okay, after a little bit of break, let's get to the last part of this lecture and this course, which is deriving the governing equation of motion using the Euler-Lagrange approach. So Euler-Lagrange approach. And as I said, none of these stuff are going to be on the exam, on the final exam, but we want to, I think we are at the right place right now that we have talked this much about vibration. Your next step after this course, I think we're at the right place to talk about this method of Lagrange Euler-Lagrange to derive the governing equation of motion. Because lots of this approach is basically valid for deriving governing equation of motion in dynamics for particles and rigid bodies, but as we will see, it is going to be used a lot for when we are dealing with oscillatory systems, because it just makes the derivation much easier. So let's have our simple. I'm gonna just state the approach for a simpler case, and then we generalize on top of that. For our simple mass and spring oscillator, so let's say we have oscillator here. It's just a spring and mass, and right now we are just considering the simplest case, that there is no damping, energy dissipation, there is no external force acting on this particle, and we have just a free vibration of this spring mass system. So let's show the coordinate system here from here, which is x, and here at x equal to 0 the spring is at rest. So far to derive the governing equation of motion, we have had the Newton's approach, which was basically sigma f equal to ma, or here, because we are in one dimension, mx double dot. And we basically saw that f here is just, we have to draw the free body diagram. F here would be minus kx, and this would be equal to mx double dot, and here we get mx double dot plus kx equal to 0. So this was the governing equation of motion, which was relatively easy to derive this using Newton's approach. So we are going to derive the same equation using Euler-Lagrange approach, and at first it might seem that it's not that different from Newton's approach in terms of difficulty or just making our life easier. But when we have larger systems with more degrees of freedom, then this approach shows its power in terms of making the derivation much easier. So let's derive this equation, this governing equation of motion for this system using Euler-Lagrange approach. For Euler-Lagrange approach, there is a quantity called Lagrangian that is defined for this system. So Lagrangian, which is defined as the kinetic energy, so kinetic energy minus potential energy, or we can show with T minus P here, which T here is the kinetic energy, P is potential energy. So this is the Lagrangian, and basically this approach says we have to construct this Lagrangian, we have to calculate this Lagrangian function, which is the kinetic energy minus the potential energy, and once we have the Lagrangian, we can derive the governing equation of motion using this equation. The derivative of the Lagrangian with respect to t, partial derivative of the Lagrangian with respect to x dot. Again, this is just for this simple mass spring system. I will generalize this as we proceed. Minus the derivative of the Lagrangian with respect to x equal to 0. So here the T minus P, the kinetic energy minus potential energy, would be a function of x dot and also x. We will see that in general this there could be also a T variable here. The Lagrangian for this 1 degree of freedom system could be function of x, x double dot, and t in general. But here, just for this system, let's derive this Lagrangian, just write down this Lagrangian and use this equation to see if we get the same governing equation of motion. So here, the kinetic energy T would be 1 over 2 v squared, which is here x dot squared. That's for the kinetic energy. For potential energy, it would be 1 over 2 kx squared. So the change in the length of the spring is just measured by x, because we are measuring x from the rest position of the spring. So whatever x we have, that shows how much the spring is either stretched or compressed, and we can easily calculate the potential energy. This potential energy is stored in the spring. So now that we have T and P, we can construct the Lagrangian and say L is equal to T minus P, which would be 1 over 2 m x dot squared minus 1 over 2 k x squared. Now that we have the Lagrangian, let's use this formula, this equation, to derive the governing equation of motion. So let me use another color. The derivative of Lagrange d dt, the derivative of Lagrangian with respect to x dot, which would be mx dot here. The 2 will cancel out with this 1 over 2, so this would be mx dot minus the derivative of Lagrangian with respect to x. So this term doesn't have any x, this term has a x here, so this would be minus kx equal to 0. And here we get the derivative of mx dot, which, assuming m is constant, this would be mx double dot. And here we have minus kx, which would be positive kx equal to 0. So here we got the same equation that we had over there, that we derived using the Newton's approach, but we derive it here with the Lagrangian approach, Euler-Lagrange approach. And basically, here we showed this for this simplest case, but using the calculus of variation, which I'm not sure if you have passed the course on that mathematics course, but using the calculus of variation, you can start from Lagrangian approach and get to Newtonian equation. You can start from this equation and derive the Newton's equation, or the other way around. You can start from Newton's approach and derive this equation for Lagrange, which I'm going to leave a link below this video that at least show you what the motivation is to kind of derive, for example, the Newton's equation from this Lagrangian Euler-Lagrange approach. So I will leave the link below this video for that motivation, for that link between these two methods using the calculus of variation. So this was for this simplest case, and here you can tell that, okay, this method is very powerful compared to the Newtonian approach. But let's go one step further and see how this approach makes the derivation much easier. If you have noticed here, for the Lagrangian approach, we don't have any vector equation. Everything is in terms of a scalar, because the kinetic energy is a scalar, the potential energy is a scalar, therefore the Lagrangian is a scalar, and here we are taking the derivatives of a scalar, which again we get our equation. You might say that, okay, for the Newtons also we had the scalar approach here, but as we go to let's say motion in 2D or 3D, the Newton's equation would be basically a vector notation. It would be sigma f, vector f is equal to ma. But the Lagrangian approach still is going to be in a scalar format. So let's say for a particle moving in a space, not in 1D, just in 3D, the position vector would be a function of x, y, and also z. So we need 3 coordinates to fully define the position of a particle in a space. And if we want to use the Newton's equation, we have to use the vector notation ma dot. But the vector, the acceleration vector. But for the Lagrangian approach, basically, we consider each of these variables, each of these coordinate along the coordinate axis as 1 degree of freedom. So this would be a 3 degree of freedom system. 3 degree of 3 degrees of freedom system, because we need 3 independent variables to fully define the position of that particle. And here, for the Lagrangian approach, we would say that let's consider, for example, x. I am moving toward the general format of the Lagrangian approach, and then we will show an example that kind of like make the comparison between the Newtonian approach and a Lagrangian approach in deriving the governing of equation clear. But let's see the difference between the Newton's approach and the Lagrange approach in terms of being a scalar, in a scalar format, and also in vector format. This is a vector equation, but here we have basically x as 1 degree of freedom. Let's just show it with q1, y as another degree of freedom, q2, and z has another degree of freedom as q3. So the Lagrangian here would be a function of q1 in general, q2, q3, and then q1 dot, q2 dot, and q3 dot. And also in general, I can write down t here. So again, this is a scalar quantity. And if we write down the Lagrange equation, it would be in this format. So d over dt, derivative of L with respect to q1 dot. We have to write down the same equation for q1, q2, and q3. So minus derivative of L with respect to q1 equal to 0. Same thing for the other 2 degrees of freedom. So d over dt, derivative of L with respect to q2 dot, minus L q2 equal to 0. And the last equation, derivative of L with respect to q dot 3 minus L q3 equal to 0. Or an easier way to show this is just to show that d over dt, derivative of L with respect to qi, minus derivative of L qi dot. Qi equal to 0 and I is equal to 1, 2, 3. So we get 3 equations, a scalar equation, and these 3 equations give us the governing equation of motion for a particle in a space in general. For a rigid body in a space, so rigid body in a space, in general we have 6 degrees of freedom. So we have to determine, for example, x, y, and z of, let's say, center of mass. Doesn't matter, any point on that rigid body. And also we have to determine the orientation of the rigid body with respect to the 3 axes that we have for the coordinate system. Let's say that we show that orientation with theta, psi, and phi. So 3 angles and 3 spatial coordinate. And basically here we can play the same game and say that x is equal to q1, y is equal to q2, and all the way to phi is equal to q6. And basically the Lagrangian here would be a function of q1 all the way to q6, and then q1 dot all the way to q6 dot and t. And then once we have this, again, we can write down the equation d over dt, derivative of L with respect to qi dot, minus derivative of L with respect to qi equal to 0, and here I is equal to 1, 2, all the way to 6. Whereas if we wanted to use the Newtonian approach, we have to use the Newton equation and also Euler equation, that are vector notation in general, for a rigid body in a space that has 6 degrees of freedom in general. We didn't go to kinetics and kinematics. Kinetics, actually, we studied the kinematics of rigid bodies in 3D, but for the kinetics, we didn't study the kinetics of rigid body in 3D in the general case. That would be a subject for advanced dynamic course, but we studied the kinetics of a rigid body in 2D, which basically we had 3 degrees of freedom for a rigid body in 2D. X and Y coordinate for the, let's say, center of mass or one point on the rigid body, and theta, the rotation along the axis that is normal to the plane. But for a rigid body in a space, generally we have 6 degrees of freedom, and if you use the Newton and Euler equation, you will learn what the Euler equation will be in 3D for a rigid body. But basically it's going to be a similar equation to what we had in 2D. And you're going to have 2 vector equations, one Newton, F equal ma, and the other one is Euler for 3D. And some people, they like using, working with scalars better. Basically, they prefer to just work with the Lagrangian method because they don't need to just keep track of, let's say, the unit vectors for coordinate access, coordinate system access, and stuff like that. But it depends on how you are comfortable with the vector notation or a scalar notation. I personally don't think that just going from vector to a scalar version of an equation is a huge plus, huge benefit. But making the derivation shorter, if there is a method that makes the derivation of a governing equation of motion for a system shorter or simpler, that would be something of interest. And now we want to exactly show that using this Lagrange approach, aside from just turning everything into a scalar, it actually makes the derivation much easier, especially when we have a system with large number of degrees of freedom. So in order to do that, let's say we have a oscillatory system that has 2 degrees of freedom. So here, or we can use 3 degrees of freedom to fully show the powerful of this method. So let's say this is M1, a spring M1, and we have K1. This mass is attached to another mass with a spring M2. And then this mass is attached to another mass, let's say M3. And here we have another spring. So this is K1, K2, K3, K4. So here, because we have the motion in 1D, one dimension, for each particle we have 1 degrees of freedom. So this would be, for example, x1, that measures the motion of mass m1. x2 measures the motion of mass m2, and here x3 measures the motion of mass m3. And here, let's assume that when x1 is equal to x1 is equal to x2 is equal to x3 equal to 0, all the springs are at rest. And we want to derive the governing equation of motion for this system. We basically say that, okay, what if, for example, we give an initial velocity or initial displacement to 1, 2, or 3 of these masses, how would the response of the system x1, x2, and x3 would be? So if you want to use the Newton's approach, let's see how hard or how easy that would be. So if you want to use the Newton's approach, we have to draw 3 free body diagrams. So for M1, and for each of them, in order to derive the governing equation of motion, we kind of like displace each mass along the positive coordinate by just value of, let's say, x1, x2, and x3, and then draw the spring forces. So if mass m1 is just moved to the right by, let's say, value of x1, what would be the force of this spring? So this would be k1 x1. What would be the force of this spring that exerts on this mass? Well, it depends on how much x1 and x2 is. If x2 is larger than x1, that means, so x2, this mass goes to the right, x1, this mass goes to the right again. And if this mass goes to the right more than this mass does, then the spring is a stretch. The spring stretch wants to just go back to a rest position, and that means the force of this spring would be to the right. So we have to say that this force would be K2 times x2 minus x1. Keep in mind that x2 is just larger than, we are assuming that x2 larger than x1. Okay, so that's all the forces in the horizontal direction for this mass. Now we have to go to M2. For M2, because this force was in this direction, M2, the force that this spring exerts on this mass would be in the opposite direction and with the same value. So this would be K2 x2 minus x1. Because if this spring is stretched, so let's say this was the initial spring and now this is the stretched spring. So this spring wants to go back to this shape. So it is pulling this mass in this direction and it is pulling this mass in the other direction. That's basically the forces that this spring exerts on these masses. And we can do the same analysis assuming that x1 is larger than x2. If you do that, I'm not going to do that, but if you do that, basically you should get the same equation at the end. Doesn't matter on this assumption, but you have to go along consistent. If you are considering x2 is larger than x1, then you have to just put these forces in this direction. If you are assuming that x1 is larger than x2, then this force would be in this direction, this force would be in the right direction. So for the other case, if x1 is x2 larger than x2, then this force would be in this direction, and you have to put, for example, K2 x1 minus x2, not x2 minus x1, because now this is a positive value, and you are showing the direction on the free body diagram. So let's get rid of this. So again, that assumption doesn't change anything, but we have to just keep everything consistent. Okay, so that's the force that this spring exerts on this mass. And for this spring, it depends, the force of this springs on this mass depends on the displacement of x2 and x3. If x3, assuming that x3 is larger than x2, then we can play the same game here, that this force should be in this direction. So this would be K2 or K3 times x3 minus x2. Again, assuming that x3 is larger than x2. And for mass M3, we have to have this force in this direction, K3 3 x3 minus x2. This is m3. And this force would be in this direction. So this would be k4x3. So now that we have the free body diagram, let me erase this. Okay, so now that we have these free body diagrams, we can go ahead and use Newton's equation to derive the governing equation of motion. So here I can write down this would be minus k1 x1 because it is in the leftward direction, plus k2 x2 minus x1. This is in the positive direction. This would be m1 x1 double dot. For the second mass, this would be minus k2 times x2 minus x1 plus k3 x3 minus x2 would be m2 x2 dot. And for the last mass, it would be minus k3 x3 minus x2 minus k4 x3 is equal to m3 x3 x3 double dot. So here we get, from the first equation, we can kind of like reorganize these terms and write down m1 x1 dot plus, so we have minus k1 x1 and minus k2 x1. I can bring those terms to the right hand side equation and factor out x1. So this would be plus k1 plus k2 x1 minus k2 x2 is equal to 0. Over here we get m2 x2 double dot plus k2 plus k3, bringing these terms to the other side, x2 minus k3 x minus x3 is equal minus k3 x3 minus k1 x1. So minus k1 x1 equal to 0. And for the last mass, we can say that m3 x3 double dot plus k3 plus k4 x3 minus x3 x2. I think here we should put also, no, that's right, x3 k3 x2, and that's it. So k4 k3 x3, and here we have minus k3 x2 equal to 0. So that's basically Newton's approach to derive the governing equation of motions. We got three ODEs, 3 second order differential equations. And the hardest part is just to keep track of these forces to go along consistent with these assumptions and draw the free body diagram. And imagine what happens if you have, let's say, another mass here. Let's say your masses are allowed to move in plane, basically in 2 dimensions. Let's say you have another mass here, then another mass here, another mass here. So then you have to keep track of x and y for each mass to say which one, assuming which one is larger than the other one, to draw the free body diagram, and then writing down the equations of motion using Newton approach. So you can see that this is kind of like cumbersome here to use this approach. And now let's derive the governing equation of motion using Lagrange approach. So for Lagrange approach, I would say that L is equal to T minus P. basically here T, the kinetic energy, would be the sum of all the kinetic energies for all these particles. So it would be kinetic energy of this particle plus kinetic energy of this particle and kinetic energy of this particle. So this would be 1 over 2 m1 x1 dot squared plus 1 over 2 m2 x2 dot squared plus 1 over 2 m3 x3 dot squared. And for potential energy, it would be the potential energy that is stored in all of these springs. And here is the good thing about this approach, is that the potential energy doesn't depend on if a spring is compressed or stretched. It just depends on the amount of the change in the length of the spring. It doesn't matter if it is stretched or compressed. So for this one, I can say that, okay, again, m1 goes to the right x1, m2 goes to the right x2, m3 goes to the right x3. And I don't need to make any assumption on which one is larger than the other one, and for the other free body diagrams. I would say that if this one goes to the right by x1, the potential energy is in this one would be 1 over 2 k1 x1 squared. If this one is going to the right by x1, this one is going to the right by x2, the potential energy is stored in this spring would be 1 over 2 k2 x2 minus x1 squared, or x1 minus x2 squared. Doesn't matter, because it is a squared. Doesn't matter which one is larger than the other one. So the potential energy would be 1 over 2 k1 x1 squared plus 1 over 2 k2, let's say x2 minus x1 squared plus 1 over 2 k3, let's say x2, for example, minus x3 squared. Again, as I said, doesn't matter. We don't need to just go we don't need to pay attention to the magnitude of these displacement. Plus 1 over 2 k4 x4 x3 x3 squared. Okay, now that we have the kinetic energy and potential energy, basically we can write down the Lagrangian. L would be T minus P, and once we have this, we can use the Euler-Lagrange equation to derive the governing equation of motion. So this would be, let's say, x dot I minus L xi equal to 0, and I would be 1, 2, 3. So far no free body diagram, nothing like that. So I can just substitute I equal to 1 and just use this equation to derive the governing equation for mass 1. So if I is equal to 1, this would be d over dt, derivative of Lagrangian with respect to x1 dot. So the Lagrangian is just t minus p, and p doesn't have any x1 dot term. So this would be basically the derivative of t with respect to x1 dot. So this would be m1 x1 dot minus the derivative of Lagrangian with respect to x1. So again, the kinetic energy here doesn't have any x1 term. The potential energy does. So we would say that this would be minus the derivative of this with respect to x1. So this would be k1, and we have a minus here, so we should put a minus also over here, because we have to take the derivative of Lagrangian, and Lagrangian is t minus p, so there is a minus over there. So minus here with respect to x1, this would be k1 x1, and here it would be plus k2 times x2 minus x1, and the derivative of inside the parentheses with respect to x1, which would be minus 1. And here it would be plus, doesn't have any derivative actually with respect to x1, doesn't have, this term also doesn't have any term, any x1 term. So this would be it basically. So we get the derivative of this with respect to t. This would be m1 x1 dot x1 double dot. Here minus minus, this would be positive k1, and we have also a positive x1 here, and here is just minus minus would be positive, so I can turn this into a positive. Let's say this is a positive, so this parenthesis we have to have another parenthesis here. So because here we have a positive k2 x1, let me write down this as k1 plus k2 x1, and we have minus k2 x2 term here equal to 0. And this is basically the same equation that we got here using Newton approach. For when I is equal to 2, let me use another color here, so I is equal to 2, the equation gives us d over dt, the derivative of Lagrangian with respect to x2 dot. Lagrangian is t minus p, this term doesn't have any x2 dot. The only term that we have that has the x2 dot is this term, and the derivative of this with respect to x2 dot would be m2 x2 dot. So this would be m2 x2 dot minus the derivative of Lagrangian with respect to x. And because we have a minus here, so we have to put another minus here. And the derivative of Lagrangian with respect to x2 would be, this term doesn't have any x2, this term doesn't have any x2, only these two terms have x2. So this would be 2k2 x2 minus x1. Here this would be 2x2 minus x3. 2k3 x2 minus x3. So this would be 2, or actually 2 times 1 over 2, that would they would cancel out. This would be k2 x2 minus x1, and here we have plus k3 x2 minus x3, that's it. And here this is equal to, we have to have another parenthesis here, equal to 0. So minus minus, here we have a positive, so this would be m2 x2 double dot plus k2 plus k3 x2 and minus k2 x1 minus k3 x3 equal to 0. And this is basically the same equation that we got for x2 using Newton's approach. Same thing for the third degree of freedom here. So I equal to 3, we get d over dt. The derivative of Lagrangian with respect to x3 dot would be m3 x3 dot minus, we have another minus here, and this would be the derivative of this potential energy with respect to x3. So these two terms doesn't have any x3, so this would be k3 times x2 minus x3 times minus 1, because the derivative of inside parentheses is just minus 1 when we are taking the derivative with respect to x3. So that would be k3, so minus k3 x2 minus x3, and the last term would be basically k4 times x3, so plus k4 x3. So here again minus minus, that would be positive, and here this would be m3 x3 double dot plus, so we are going to have k4 or k3 plus k4 x3 minus k3 x2 equal to 0. And this should be exactly the same equation that we got from Newton's approach. So you can see that using the Lagrange approach, all you care about is just the kinetic energy, the potential energy, and the rest of it is basically taking derivative. You don't need to worry about the right direction of the forces, making consistent assumptions, and drawing the free body diagrams. So that's the power of this approach. And basically solving this system of equations, so here, this would be another thing that you will learn during the mechanical vibration course. We call these systems multi-degree of freedom systems. And basically you start with the 1 degree of freedom system over there, add damping, add external forces, and then once you're comfortable with that, you just consider more degrees of freedom, which you get system of ODEs. Instead of just one ODE, you're going to get system of ODEs that are actually here coupled to each other. Because in equation on x1, you see term x2, and on equation on x2 double dot, you see term x3 and x1. So you have a system of coupled linear differential equations for multi-degree of freedom systems. And here we showed this approach, the Lagrangian approach to derive the governing equation of motion, when we didn't have any basically damping or external forces on the system. But you can imagine that with a slight modification, this equation could be generalized to derive the governing equation of motion when you have non-conservative forces, like damping force, which dissipates energy, and also when you have external forces that basically you consider them as non-conservative. If they are conservative, everything is okay. But if they are not, so you are safe by considering them as non-conservative forces. As I said, the only forces that we consider as conservative here in these kind of problems is just the spring force and also the gravity. We treat the other forces as non-conservative forces. So there would be a more generalized format of this Lagrange equation that basically has a term here on the right hand side that is associated with all the non-conservative forces, all the external forces on the system. But that's something again for just mechanical vibration. The left hand side is going to be similar, and you will learn also during the mechanical vibration course how we add the external forces in this approach. And these QIs, they are called generalized coordinate. So these are generalized coordinate basically. That's a name. So I think with this Euler-Lagrange approach, we are at the end of this lecture and also at the end of this course. So I think that's it for this lecture, and just a couple of notes on the final exam. So I think the final exam is on this Thursday, coming on this Thursday. I'm gonna post an announcement on how the format of the final exam would be. Basically, it's going to be in the similar way that we did the midterm exam. So I'm gonna be posting the questions on the right time over my course website, and then you guys have time to solve that and then take a picture or scan your solutions and then send it to me. It is important to just you make my work easier if you just number all the pages and write down your answers in a clear way. We're gonna have all the restrictions that we had for the midterm exam, including that there is no laptop, no calculator allowed. I'm gonna be posting the detailed instruction for the final exam, and the final exam would be on the stuff that we have had since the midterm, after the midterm. So the first part of the course that was covered in the midterm exam, the later part of the course that we have had so far is gonna be on the final exam. As I said, these kind of like introduction on mechanical vibrations, the stuff that I introduced on nonlinear dynamics, this Euler-Lagrange approach, they are not going to be questioned on the exam. This is kind of like your transition from this course to future course that you're gonna have on similar topics. And what else? Oh, for the solution of the homeworks, so I'm gonna be posting the solution to homework 4 probably tomorrow. The homework 5 is due on Tuesday on 5 p.m. So please submit your solution on time so that I can post the solution for homework 5 after the deadline, so that you can have at least 1 day, 2 days before the exam to take a look at the solutions. So although in the past, if you send me your solution just a little bit late after the deadline, I would be fine with that. But here for homework 5, please do submit your homework by the deadline so that I can post the solutions for the class so that your friends can use it. So please try to stick to the deadline for homework 5. So I think that's it for this course, and I wish you guys best of luck for the final exam and also in the other courses that you have. This was a very unprecedented time, and it's just, this happened during our lifetime, probably just once, hopefully once during our lifetime. And we all, hopefully we all get through this, and hopefully you're gonna have a successful final exam week in this semester. So that's it. Good luck with your final exam.